Hi AP Stats, this is 11.2 notes, part 1. We're on chapter 11, so that is all about using chi-squared tests. So let's review. We just finished the goodness of fit test. That was the M&M one with its color distribution, right? So we've already done that one. So today our big one that we are going to focus on is our test for sameness, homogeneity of populations. Okay, so in this one, we're going to be looking at one variable, but in two or more populations or treatment groups. So if we took our M&M example, it'd be like comparing M&Ms from this year, their distribution, to our distribution from 20 years ago and seeing if they are the same or not. We'd no longer be looking at what the percentages is that M&M and Mars gave to us. We just want to compare what it looked like 20 years ago to now and say, are they alike? Are they the same thing? All right. So keywords for homogeneity are usually the idea of are they the same or has something changed? What else? And they give us an example there that has to do with Canada, another one from US, and we're trying to compare something about students between those two. Cool. All right, so that's the one we're going to work on today. This one's going to be a bigger table. It's not just going to be one row of data. We're potentially going to have lots more rows of data for these. So when we get there, this is our calculation for our expected counts on a table. We're going to take the row total, the column total, divide by the grand total. Our chi-squared statistic is still exactly the same. It's still observed minus expected, squared that over expected. Our degree of freedom has now changed. Before it was categories minus 1. Now it's row minus 1, columns minus 1, and you multiply those together. Conditions are still the same. Expected cell count should be at least 5. It's okay if there's one item in the entire table that's just slightly less than 5. You just note it and say, we'll continue, it's good enough. And this one that we're doing today, we can also do as a 2-sample proportion test. It's just really tedious because we'd have to do it for every single category. So like if this was M&Ms, we'd have to run a 2-sample proportion test on reds, then again on orange, then again on yellow, then you get the idea, right? So chi-squared lets us handle it all in one humongous test. Right, so let's take a look at an example. We're going to go through the M&M example this time. We'll do a test for homogeneity using chi-squared. So now our example is not about what did M&M Mars say the distribution was, but we now want to compare. And so the question is, are the color distributions the same from 5 years ago and now? So we have our two-way table of our counts, the ones we did in the last lesson, and then I pulled up the ones that I did for a class activity 5 years ago and put those in there too. Notice that the totals are not all the same, right? There's a 60, there's a 50, right? So we do want to acknowledge when we fill out a table that you do all the totals, column totals, row totals, we're going to need them all. So one of the things we want to do that's new is we want to include a expected count table. So if our original table was 2 rows, our expected table will be 2 rows. If our original table was how many across? 1, 2, 3, 4, 5, 6, then our expected should be 6. So basically you're going to create another table. Just make sure that you tell them one of them is the observed and one of them is the expected. Okay, so I might even write on this one that this is the observed. Okay, so then the next thing I want to do is I want to fill in what the expected counts would be. So remember when we did this with the M&Ms in the first case, we had the percentages to use and we just redistributed the 60 M&Ms based on the percentages. Well, here we're going to take these and we're going to redistribute them. So the way that these work is you're going to be doing row total times column total divided by grand total. So in our case for the first blue, the row total is 60, the column total is 19, and the grand total is 110. And that's going to look just like the one right next to it, which was 10.36. And we do this for every single one. So you'll notice, right, this is a 60 for the row, a 22 for the column, and then they're always divided by 110 in this table because that's our grand total for the table. Okay, I left another one open just so that we could go and show and practice this one as well. So our row total for this one is 50, our column total is 19, all over 110, right? And that should give us the 8.64 again. So now I have all my expected counts listed here as well. So when I write it up, I can say, just go look at the expected count table. All right, so here we go. Again, there's no confidence intervals for these, just significance tests. Okay, so do we have convincing evidence to conclude that the color distribution has changed from 5 years ago? So remember, that's going to be our alternative hypothesis. So our original hypothesis, or null hypothesis, is going to be that they are the same distribution. And then we're going to be comparing it to not the same. Notice there's no proportion equals, there's no mu equals. We're using the words, the sentences for this one. Same 3 categories again. We're looking for where did the data come from. In this case, they came from 2 completely independent samples, right? We have the one from current, the one from 5 years ago, so we're good here. 10% rule. So we are still sampling without replacement. So in our original one, it was 60. We believe there's more than 600 M&Ms right now. And 5 years ago, 10 times 50, we're pretty sure there was more than 500 M&Ms 5 years ago, right? So it seems reasonable that these would pass the 10% rule. The large count rule now is that we want to make sure everything, and it's in the expected counts, it's not observed, it's expected, need to be at least 5. So all you have to do is create that table, and then you just tell them what your lowest count was. Our lowest count was 5. Okay, and if there happens to be one that was 4.9, 4.8, you could write that and say, there was only one that was 4.8, really close to 5, we'll continue. All right? Okay, onwards, expected counts. I'm going to say that those expected counts are in the table above. Go look and go find them. Okay, next one is, what is the name of this? Our name for this is the chi-squared test for homogeneity. We put in the alpha level just like before. If they don't tell us, it's 0.05. The formula for chi-squared is the same as well. It's still observed minus expected, square that difference, and then divide it by the expected count. And then that sum symbol in front says we're going to add them all up, right? So in the first row, we had a 9 for the observed. And then in the expected, it was 10.36. And then in the next one, right next to it was 8 minus 10.36, or yeah, 8 minus 10.36. And I have to go through both rows. So there were 2 rows of 6 each. I'm going to go through every single one of those. Now, the one thing that they do allow is as long as you show the setup for the first 3, you can use that plus ... and then show the very last one on the last row on the far right, and then do our total. So I'm going to let my calculator now do this for me. So this is going to take a little bit of setup. So the first thing I'm going to do is I'm going to turn on my calculator and I'm going to go to a new place that we have not done before. You probably haven't done this in any of your math classes. We're going to go to matrix. It's this blue one here. It's the 4th button down right there. And when you see it, it's just going to be a whole bunch of letters in brackets. So we're going to go over to edit. We're going to open up the first one. And the first one wants to know what size should I make it. So remember, if I did size for these, it was 1, 2, 3, 4, 5, 6 by 2. So they want to know how many rows first. So usually I'll end up entering this actually backwards. And you can tell that because the second I do that, you can see how there's only 2 across, but it goes 6 down. You're like, I put them in the wrong place. Okay, so we're going to switch them around. It's always row first, how many rows, then how many columns. And now when I do it this way, I can see that it's going to continue to the right. So this is our observed count. So I'm going to put in those original ones. So that's a 9 first, then the 8, then the 12, then the 15, the 10, and I just keep pressing enter between them and it takes me to the next one. Okay, so after I did 6, it wrapped back around again. So now I'm doing the second row. So I'm doing 10, 11, 10, 6, 8, 5. And once again, this is my observed, not my expected. Okay, so once I'm done here, we're just going to press second quit, and we're back out to the main screen. Now we're ready to actually run the test. That's all it needed in there. So I'm going to go over to stat. I'm going to go over to tests. I know it's near the bottom. It is not goodness of fit test. Goodness of fit is the only one that works with lists. So we are bigger than a list. We are now into tables. So that is C, chi-squared tests. And when I hit on this one, it's going to say where did you store your matrix of information? So our observed is in A. It's going to fill in B for us. They just want to know, where do you want me to put it? So why not put it into matrix B? And we're going to go down to calculate. and it's going to give us all the important numbers for our test, just like every other time we've ever run this. So I'm going to go fill those in so I make sure I have them, and then we're going to come back and look at what the expected table looks like. Okay, so I know that if I add these all up together, it says it's going to be 4.002. So remember, our chi-squared, right, is skewed to the right, and its degree of freedom is going to be the number of rows minus 1 times the number of columns minus 1. So we still have a degree of freedom of 5 on this one. And now I'm going to do 4. So I'm going to be like right to here, 4.002, and I'm going to color in all of this stuff all the way over. So I want to calculate the probability that chi-squared is greater than 4.002, and that would mean I would be doing a chi-squared CDF from 4.002 to infinity with degrees of freedom equals to 5. And they are telling me on my screen that that should be a probability amount of 54.9%. So because our p-value, which is 0.549, which is huge, is greater than our alpha level of 0.05, we fail to reject. So this is all the same, right? Fail to reject HO. That means we do not have convincing evidence to conclude that the color distribution has changed. Seems like from my numbers 5 years ago, we're still pretty much using the same color distribution that they were 5 years ago to now. So there is our conclusion. So notice that I did all of the math up here when we did these, right? I showed you how to find all of the expected counts, okay? However, and you do need to know how to calculate them. So you do need to know it's row total times column total divided by grand total. But after I run the test, so we've done this with contribution on GOF tests. We've done this with residual when we're doing a best fit line. When you run this one, it does store your expected counts in the other matrix. So I'm going to go down to blue matrix again. And notice that now B has been filled in to be the same size as A. And if I go over to edit and I move down to this one and I press enter to just look at it, it has already filled in the exact same numbers that I needed for my expected count. So I could go back and check a few of them. Okay, you will need to know how to do the formula for these. They will ask you to do a few of these by hand instead of doing the entire thing. Okay, so you should know how to do this by hand. But again, if we're just doing a significance test and we have it all, it's all right here. Now I could show them a few, show this calculation, this calculation, this calculation, and then after that, I'm just going to start filling in the numbers. Okay, so the next one would have been 11.455, right? And I could use this to go ahead and fill in the rest of my values. Cool. All right, so pretty straightforward, pretty easy. Again, this is the one that could also be done as two sample proportion test. It would just mean that I'd have to rerun this test for every single color proportion to do that. All right, that's it. We'll see you on the next one.